In this lecture, we're going to talk about memory. Specifically, we'll learn about different memory technologies, what the memory map is, and then we'll work some problems on how we can build memory from smaller chips, and then we'll also talk some about tri-state devices. Okay, so first, memory is a really important subsystem for a computer. Remember, in our last video, we were talking about the von Neumann architecture, or a stored program architecture, where the memory holds both the data and the program. Now, there are a lot of important architectural design features, as well as different types of devices that are used to create memory. And we're really only going to start scratching the surface in this course. Okay, so at a high level, this is the way that we can model a memory. So the basic operation of memory is that it's a piece of storage. It's storing some memory. And the interface to memory for many computing systems looks like this. So there are some bits which tell the memory the particular address in the memory that we'd like to access. There are some bits that control the action of the memory, for example, reading or writing. And then there are some bits or a bus which are used to send data into and out of that memory. And with this abstraction, there are two key operations for the memory. Reading, where we want to get some information out of the memory at a particular location or a particular address. And writing, where we're actually going to put some data into that memory at a particular location. Now, a memory has some capacity or can store some amount of information. And if the address bus has m bits, this means that we can have a total of 2 to the m locations in this memory. Or if you think of it like a table, there are 2 to the m rows in that table. Now, each location in the memory can have some number of bits. And if, say, each location or each word in the memory had s bits, then we would say this memory is of size 2 to the m by s. Okay, and so there are many different types of memory, but we broadly classify the memories in two types. There are memory that are read-only. An example of this are EEPROM devices. There are memories that are used for both reading and writing, or RAM, stands for random access memory, and a good example of this is DRAM and SRAMs. And then there's also some other different types of memory, hybrid type of memory technologies like flash. The underlying technology and circuits for these different types of memories also reflect how they're used. So ROMs tend to be non-volatile, meaning that if we remove the power from the device, we still maintain the data, while RAM tends to be volatile. If we remove the power, reduce the voltage to 0 for the device, we lose our data. Okay, so to implement a ROM in HDL, we could do something as follows. So say I wanted to build a 16 by 8 ROM, meaning it has 16 locations. Each location has 8 bits. So the bit length or the word length is 8. So with 16 words in this memory, I'm going to need 4 bits on the address bus in order to identify the word that I'd like to read. And the data bus out will have 8 bits. So in System Verilog, so I'll have a bus with 4 bits for the address and an output bus, 8 bits for the data. We can declare in System Verilog a memory using this syntax. The numbers in the bracket before the logic name, in this case ROM, tells us the number of bits stored at each location, and the bits in the brackets after the name tell us how we address the memory and what the capacity is. So in this case, there are 0 to 15 locations. Each location has bits 0 to 7. This initial block then is a way that we can initially load the ROM in our HDL design. In this case, it's reading from a text file with this .mem extension, 8-bit values, 16 8-bit values. And we can write in any memory location. These last two parameters are just which address I start with and which address I end at. Then the always block at the bottom here, this is a block where the synthesis tools will infer that I have a flip-flop, this underscore FF, and it's changing on the clock edge. So this read is going to occur at the positive clock edge. And I'm reading from the ROM at the particular address and putting this on the output data. You can also make a ROM that's asynchronous. So in the case on the right, I have an always combinational block that as soon as the address changes, we'll put something on the output. In this case, it's a hard-coded values. In VHDL, you can do something very similar. Now for a RAM, remember the big difference here is that now I can also write to the memory in addition to reading from it. So with our block diagram on the right, we want to create a 32 by 4 RAM. It has a input bus, 4 bits for reading the data, and a 4-bit output bus, D out. I'm going to need 5 bits of address to specify the location in the memory that I want to read or write from. I'll have one input into the block for enabling it from writing. Otherwise, we'll assume we're reading. And then obviously a clock. And in this case, we're going to design our circuit so that our writes are synchronous and our reads are asynchronous. So now on the left, we have our system Verilog code. It's parameterized, so I could change the bit length or the word length. In this case, the default is 32, and the number of bits of address that come into the blocks. In this case, the default is 6. So if I wanted to instantiate a RAM module that matches my diagram here on the top right, I would write something like this. So I'd like a RAM, and the parameters, in this case, I have 5 bits of address, and my bit length is 4. Give it some name, and then I'll connect ports. Okay, now within the RAM module, again, we see the same thing here as we did before with the ROM, declare the memory, and for reading from it, it's asynchronous, so whatever the address is, we're going to put that data onto the output, and then we're also going to be doing, in parallel, the writes, but this is going to happen on the positive clock edge. We're going to write the data into the memory location that's specified by the address and ADR. And this is only going to occur if the write enable is on. Okay, so a little more background on some of the major RAM technologies. Static RAM, or SRAM, is used in systems in many different ways. One place it's used extensively are on different levels of cache within processors. And these are usually made up of several transistors on the order of maybe 6 or 7 transistors. And they have a nice property that they're very fast, both for reading and writing. They are volatile, however, so if we remove the power, then we're also going to lose the data. Now, this is different than DRAM or dynamic memory in that with a DRAM, we can essentially get away with storing a bit of information on just one transistor. And we're using that transistor essentially as a capacitor. This means that we can get much larger density and much larger capacity at lower cost using DRAM technology. But as you can probably guess, the downside is when I store information as a charge on a capacitor, the thing about a capacitor is they discharge. And so I also need to periodically refresh the DRAM. This is logic that's included in the circuitry associated with the DRAM module. Today, DRAM has been used for a while now as the major main memory of computing systems. But because of these limitations with refreshing and being off chip, they tend to be much slower, hundreds, if not thousands of clock cycles to access versus static RAM, which is the reason why static SRAM is used more for on-chip caches. DRAM is also volatile, so if I remove the power, then I lose my data. The third major technology, which has improved a lot in the past years, and we're likely going to see even more types of innovation, is in the area of non-volatile memories. An example of this is flash. And like RAM, you can both read and write. For many systems in the past, it's mostly functioned as a ROM because it has this characteristic that it's actually much easier to read, much faster to read than it is to write. The writes tend to be very slow. And this is because of the fact that you can't just rewrite individual words. Instead, you have to write entire sectors when you want to do writes. This has been improving, however, and it's very likely going forward, non-volatile memory might, in fact, start to replace DRAM technology as the main memory of computing systems. It also has this nice property that it's non-volatile. You remove the power and you'll still maintain your data. For that reason, it's been used for a long time now for storing data that needs to be saved across power cycles. So you can think of memory as being unclocked, although it has a clock, but in modern systems, it can take many CPU clock cycles to actually get access to the data that you want. And so an important metric which memories are evaluated against are their access time of read operation, which is the max time from availability of the address input until the data output's available, and also the write time. Well, how much time does it take from the availability of the address until the completion of the actual write? Okay, so this shows an example block diagram of a RAM. Many memories are built using these smaller cells, and this is true for RAM. So this is an 8x2 RAM built out of these smaller 1-bit RAM cells. And decoders, and this is a standard decoder, which hopefully you remember from 133. It's one of the places where actually we use decoders a lot in digital design. In this case, it's an 8x2 RAM. I have 3 address bits. The 3 address bits feed into a 3 to 8 decoder, meaning that whatever the bits are in the address lines, I'm going to enable or activate one of these rows, and the rest of them are going to be disabled. So if my address is 2010, then I'm going to select this, in this case, the third row to either read or write from these particular RAM cells. Another important concept related to using memory are the memory maps. So when we split up data across these different smaller RAM cells or chips, it's important to be able to find out and figure out which chip has the data that we want. And this is essentially what a memory map is. It's telling us where data is stored at, different data is stored in the memory. So let's do an example. Let's say I wanted to figure out the addresses where each address goes into each segment for two example memories shown here. So on the left, I have a 128 by 8 memory built out of two smaller 64 by 8 memories. And on the right, I have a 32K by 16 memory built out of 4 smaller 8K by 16 chips. Okay, so let's start off with the one on the left. So let's assume for both of these that the first address, the first location, each of them is the 0 address. So we'll calculate this in hex. The first address is 0, and I have 128 bits. 2 to the 7 is 128, so I'm going to have 7 bits, which in hex I can specify 2 hex digits. So I have 0x, which in hardware or software, 0x is the common way that we specify if the following digits are in hex. So the first address is 0x00, and then the last location in this first 64 by 8 chip is going to be address 63. Now 63 in hex is going to be what? Well, I know that 64 is 2 to the 6, so address 63 will have 6 ones at the end. In hex, this is 3F. The very next address will be stored in the first row or the first location in the next 64 by 8 memory chip. So this will be in hex 40. And the last location will be 127, which is 7 ones, or in hex would be 7F. Now, for the 32K by 16 memory, how many bits of address am I going to need? Well, 32K is equivalent to 32 times 2 to the 10. 32 is 2 to the 5, which is the same thing as 2 to the 15. So I'm going to have 15 bits of address for this 32K memory. The first chip will have, again, start at address 0. I have 15 bits, so I'll have 4 hex digits. The last address, the last location in this smaller 8K chip is going to be, we can calculate, an 8K chip has 2 to the 13 locations, and so I'll have 13 ones at the end, which in hex is equivalent to 1FFF. The very next location will be the first address in the next chip, or a 1 followed by 13 zeros, which in hex is 2000, and then a 1 followed by 13 ones is the last location, so 3. And the next location after this would be 1, 0, followed by 13 zeros, or 400 in hex. And then the last location would be 1, 0, followed by 13 ones, which in hex would be 5FF, and so forth. And so we can see the solution here. The last chip would be from 6000 in hex to 7FFF, which is 15 ones, the last location in my larger memory. Okay, so there are different ports, different types of names for ports, depending on the memory chips that you're using. In general, we will use this type of model for our memory, though. We have obviously a bus for the address, some bits. In this case, it's a 256 by 8 RAM. So I'm going to need at least 8 bits to specify the location in the memory, and a bus for the data, and I could have a data in and data output bus, or in this case, it's bidirectional, but for both reading and writing using the same bus, and it's 8 bits. I'll have a control signal. In this case, it's active low, and I can tell this by the bar over top of it. So if I have a 1 on this control signal, the chip will be turned off, and I'll have high impedance on the output, and I'll talk more about this in the next slide. Or if it's a 0, I've essentially enabled the memory to act either reading or writing, and the write, again, an active low signal because of this bar over it. If it's a 0, then I've enabled the write, and the data that is on this data line will be written into the memory specified by the address.